All right, it is time to resume our work on the Game Boy decompiler and disassembler in particular. When we left off, we were able to disassemble, prove that we could disassemble exactly one instruction. I left with a code base that was a little dirty. I made some cleanups, fixed some namespaces that had been accidentally introduced. And I also looked at the missing or non-implemented mutators that we now need to implement. And I decided to actually adhere to the test-driven philosophy. So we're going to look at the remaining instructions. I created a bunch of unit tests for them. So we start with the unit tests, and then we run the unit tests, and I will get a red bar, and then we'll go ahead and fix them. So the instructions that are missing are instructions that consist of addressing modes, in particular these exciting ones with post, increment, and decrement. Then there is this new type of operand, a conditional operand, which we have to implement. We have an instruction called stop. We have these 2-byte instructions that we need to implement to support the bit set reset instructions, and also making sure that we're formatting hexadecimal numbers correctly, and both bytes and words need to be formatted correctly, and a couple of new addressing modes as well. So there's a few features that we need to implement, but these should be fairly quick to implement. So I'll just start and running all the unit tests to see what is working and what is not. And not a lot is working. The stop instruction is. So let's just start with this one. So why is bit not working? Well, the bit is not working because CB, which is the extension opcode, has not been implemented yet. So we need to implement that. So let's go to the disassembler and start pounding this out. And this need to get to the Game Boy disassembler. So we'll take a look at the CB opcode decoder, and we'll notice that it's invalid. So what does this decoder need to do? Well, we cannot call inster immediately because we need to read another byte. So we're going to create another decoder called prefix decoder, which will read 1 byte, or attempt to read 1 byte, and if it succeeds, then it will dispatch onto the second table of opcodes, which is this section here, the CB decoders. So let's create a we'll create a new decoder subclass, which will be private to this disassembler. And the prefix decoder is a decoder. And decoders need to implement a method called decode, which does the actual work. And what we'll need to do then is, in the constructor of this decoder, we will specify the sub-decoder that it needs to invoke once it has read the second byte of the instruction. So there will be a sub-decoder. Let's get rid of this clutter. We have an alias set up. Okay, so So when the CB byte is encountered, we execute this, and now we need to read the next byte. So we'll do if not dasm.reader try read byte again. Out comes the second opcode. And if that fails, then we ran out of bytes, and so we have to return false to indicate that this is not a valid instruction. Otherwise, we're in good shape. We have the new instruction, and now we'll use the subdecoder to decode that. So we'll just return the result of the subdecoder decoding this new byte and passing in the disassembler state. So that should take care of that, because we've already done all the work. Oh, I'm sorry. My mistake. This is not a mutator, it's a decoder, and decoders always return instructions. So we have to call the create invalid instruction method. Let's make sure that's implemented. It is. So if we ever call this method, we return a GameBoy instruction with the instruction class set to invalid and the mnemonic set to invalid. Great. Okay, so we're in good shape. If we go down and look at the decoder for, say, one of these bit instructions, you'll notice that we're using the intrinsic or the implicit mutator to generate an implicit constant, and then we know that the register mutators are all working. So if we run bit now, this should succeed. Oh, still failing. Alright, so now we'll need to debug and see what's going on. Oh, we have to actually call. We actually have to call the, or use this new prefix decoder. So let's do that. There we go. That should work. Now, one of the great things about using unit testing for this... Oh, we blew up. Now, why is that? Ah, okay. It's unhappy because we have not implemented memory operand. Okay, so this was a question that came up after last night's session. How do these renderers work for the different operands? So we'll have to implement one for memory operand, and we'll do it in TDD fashion. We'll just implement enough to make the test pass, but we'll probably have to keep making changes to do render as we encounter more and more unit tests. And this is what I like about unit testing, is I need to develop only the piece that I need to make the test pass. But then when the next test fails, I have a unit test in place that will guarantee that I won't break the old code with any changes that I make. So here we are receiving a memory operand, and let's take a look at what we're trying to... Okay, so 66. Let's just make sure that we are in agreement with the specs, because I want to make sure that we're not... What is 66? 66 is... Ah, okay. Alright, so it's bit 4 HL. So there was a bug in the unit test. So let's fix that. It should be this. Alright. So here we're expecting an HL register. So in our implementation of do render, we'll do the following. We'll render a open paren first of all, because that's what the instruction looks like. And then at the end, we'll close the paren. And then we'll need to make sure that there is a base. So if there is a base register, then we will display its name. And that should be end of that. And then we'll continue to throw an exception in this case, because we haven't implemented the other case. All right. Now then, will that pass the test? Alright, so we have a redundant 0 there. I'll accept that for now. We may change that later. But this is in essence correct. Great, so we have one passing unit test. Next, so here we have another opcode. This is the conditional jump on the 0 flag, and the jumps on this processor, when they're long jumps, that is 16-bit jumps, they're actually absolute addresses. So the address in little endian is BA98. So this test verifies both that we know how to support these conditional operands, and also make sure that the address that we decode is correct. So we need to create a new type of operand which contains a condition code. So we need to define these condition codes for this architecture. So we'll create a new class called condition operand, and it's going to be a machine operand. And the machine operand will have a do render, and it will have a constructor which will take a condition code, and the condition code that we need to define the condition codes for this architecture. And the size of this operand is really not interesting, so we'll just send a primitive type byte to the base. So what is a condition code? Well, it's an enumerated type. And we saw there is a no carry, there's a carry, there is a no 0, and there is a 0. Those are the 4 condition codes of this CPU. So we need to hang on to that. In a property. And then when we render this thing, all we need to do is just turn the condition code into a string. So we'll just call render write string condition code to string, and then to lower. Alright, so that creates a condition code. So now we'll go back to the disassembler, and we had 4 different unimplemented condition code handlers. They're right here. So they're all doing pretty much the same thing, with a different one single difference is the actual condition code. So it makes sense to create a mutator generator here. And I like this name a lot better than the chip number. We're going to call this C code. And we will require a condition code, CC. And what this will do is it will create a lambda that, when invoked, injects the particular condition code into the operands of the instruction currently being disassembled. And because it's a constant, we can create the operand outside the lambda so we don't hit the garbage collector that hard. Alright, so we have an operand, and now that gets cached in the closure of this lambda, and then when the lambda gets invoked, all we need to do is say dasm.operands add my operand. Return true. Okay, so then we can change these guys to mutators. Let's make them read-only. And so Z will be C code, condition code Z. And then the carry and let's just do them like this. Okay. Nice. Okay, so that should take care of those. And we should be able to run this now and see what happens. And my machine is a little slower than yesterday. But look, that passed, so we're good to go. Next instruction then is similar. 18FE, let's verify that 18 is the correct opcode. 18. It's 28, that's the conditional one. And it's no carry, so it should be 30. Okay, so let's fix that. So 30FE, and this would test that the relative jump is correctly implemented. The FE that we see here is interpreted as a signed byte, as you recall from last time, and that is -2, which is exactly the length of this instruction. So if the disassembler is correct, then this would create an infinite loop, because this instruction would be jumping to itself while the carry flag is clear. So this is now failing because we were implementing the wrong, we had specified the wrong opcode. So let's try that again and see whether that makes any difference. Another unit test passes. This feels great. Okay, so now we get to implement the inc opcode. And in order to do so, we're going to have to mutate our memory operand class. So let's take a look at that. Today, the memory operand class, it knows that it's base, it knows that it's offset, but there's no indication of whether it is a post increment or post decrement. So there are many ways of doing this. We could use an enum, or we could just use a boolean for each of the two possibilities. I'm going to choose booleans, but clearly that could be changed if somebody really cares. So we'll add this post increment flag, and we'll have a post decrement flag. Now clearly it's an error if both of these two flags are true. So we could, of course, add an assertion in the code to highlight this, maybe even trap the setter. But it's unlikely that our disassembler is going to get this wrong. So I'll probably just do an assert in here. Saying that it's not true that posting, oh, I'll just change the logic. So post increment is either post decrement is false or post increment is false. That always has to be true. And the likelihood of that ever happening is very, very low. But it does mean that if the post decrement bit or flag is set, we want to render a plus. So, sorry, post decrement we want a minus. So if post decrement, then renderer right char minus if we have the post increment, oops, we want to write a little plus sign. Nice. Okay, so now our decoder, when it encounters this addressing mode, it needs to generate or set these flags. So let's go to the disassembler and look at the decoders. Here they are. So they're going to be very similar to the MHL one, except they need to, in addition, set the bit. So let's find the MHL mutator, which is here. And we will basically steal this. All occurrences of this addressing mode only access bytes. I verified that already. So we do this, but this is an increment, so now we need to say post increment is true. Gets rid of that. And then decrement is going to be very similar, except we do a post increment false. Or sorry, post decrement true. There we go. So now let's see if those two instructions are correctly implemented. Let's run them. One succeeded and one failed. So this could be an error in my writing of the unit tests. Let's take a look at that. I wrote 2A. Oh, it's a copy and paste error. I wanted a different operation than the 2A, but I forgot to update the copy. So let's take a look at that. So 2A was over here, and what I wanted was the one called 3.2. Alright, so let's fix that and run that test. And again, the unit tests are keeping me honest here. Great. Alright, next. So here it's complaining because we have not implemented the absolute address mode. We can take a look at the test real quick. Yeah, so we have this absolute address 1234, and it's expected to be rendered like this. So we're using the Intel formatting rules, which specify that hexadecimal numbers are suffixed with an H, and if the first digit of the number is a 0, an A, B, C, D, or F, then we have to prefix it with a 0. So we need to do some work here. So the first thing we'll do is convert the hex string to a hex number, the integer to a hex number, and then check to see whether it is it requires a 0. So we'll go to the memory operand for that, and then we will render the offset as a hexadecimal number. So S offset, the string version of the offset, is the offset to string in hexadecimal. And then if the string A, B, C, D, E, F contains the first letter of S offset, then we need a prefix with a 0. So then we'll render a right character. We'll write an initial 0, and then we'll chase it with the string version of the offset, and then we'll chase that with an H. Great. So let's try that. Green bar, love it. Okay, next. So here we want to render immediate values the same way. Now, the immediate operator is a class that comes with the standard implementation, or the core library of Reko, but every architecture will want to render immediates in different ways. For instance, the Motorola 68K will want to render them with a hash sign in front. And so the way to implement that is to override the rendering of individual operands inside of the instruction class itself. So let's go find the instruction class, which is GameBoy instruction, and we'll override a member called render operand. So this gives us a first shot at rendering operands if we don't want the default renderer of that particular class to do the rendering. So we'll check to see if this is an immediate operand. And if it is, then we'll take over the rendering, and we'll pretty much do what the memory operand did. We'll just, in fact, this is common code. So where do we put this common code? Let's create, we'll do this. And then we'll refactor this to a method, and we'll call it render intel hex number. Okay, and I'm going to put that on the instruction actually. So GameBoy instruction dot render intel hex number, and then we'll steal this from here and put it in here, and that way everybody can share. Let's make that a public method. And I'd like to swap the order of those two guys because I prefer the input parameters to come first. So the sort of data going in is the integer, and where the output is going is into the second parameter, the renderer. It's just a personal preference. Alright, so if we have an immediate operand, then what we want to do is take the immediate operand and turn it into an integer. So we go to the im, and we get its value, and we coerce it into an unsigned integer, 32-bit integer, and then we'll convert that. Oh, what am I doing? And then we'll call render intel hex number, and we'll cast that to an int, and then we pass in our renderer, and we're good to go. Otherwise, if the operand is not immediate operand, we will just fall back to the default behavior. And so now we have implemented Intel style rendering of immediates. This will also clean up the bit that we have up here. Remember that it had an extra 0 there. That 0 will now disappear. Yes, another green bar. Great. Next. So here's another addressing mode. It's an addressing mode that uses the C register. So we need to implement that. And this one, just as an aside, this is a little bit misleading. It's not actually using the C register only. It's actually implicitly adding hexadecimal address FF00 to C and then performing the dereference. But the assembler syntax looks this way because all the input and output devices on the Game Boy are apparently mapped to a memory region that starts at FF00. So anyway, so we'll implement that. That's another addressing mode, and we'll need to create a mutator that knows how to generate them. We already have the scaffolding, so we'll just steal this guy here and then look for m_c over here, and let's group this guy with the other memory dudes. Great. All right. So now that test should pass. And the interesting thing now is that we have covered pretty much, well, almost all of the instructions now. Really just need to do these final few and then we're done. Okay, this is looking great. We have one missing instruction, LDH, here. I did think there was one more though that had a very strange addressing mode. So let me go verify that we have the last one. We don't. Okay, so the one instruction that I'm thinking of here is this bizarre one. Well, it's not bizarre, it's just uses an addressing mode that I haven't seen on the Z80 before. This is adding an immediate value to the stack pointer. So what this does in essence is calculates the it calculates the address of a stack variable, and or actually no, it's just incrementing the stack pointer by a small immediate value. Question is that a signed or an unsigned value? And I guess we'll have to take a look at the documentation for that because this does not exist on the Z80. So let's take a look and see if we can find the docs for that. Add SP. So it is a signed number. Okay, that's good to know. I would have missed that. Also, this addressing mode needs to be implemented. It also is using a signed offset. So we'll need to implement 2 unit tests for E8 and some signed offset, and then F8 and some signed offset. So let's go ahead and do that. We'll use this as a scaffolding. So this will be the add SP signed byte, and that was E8. So E8 and then some signed offset like FC perhaps, and that's going to be add SP. So this is going to be a signed number now, and that's going to be a little bit of trick because previously we just implemented an immediate operand and there we actually render the number unsigned, but now we have to check to see whether this operand is signed, and in that case we render it as a signed offset. So we'll need to fix that. But first things first, we need to set up our test. So this is going to be -4. Okay. And then the other instruction that we wanted to implement was F8. All right, so F8, FC, that's going to be a load HL with, and how is the syntax of this? It is a new operator. So this is actually computing the address of SP minus 4 and then adding it to HL. Okay. So, so this is going to be load HL. All right, so this is going to require a new mutator. This is going to require a new mutator. So let's go back to our disassembler and look at our mutators. Let's make sure that we have two separate mutators for these because they are different. F8. So this is computing a sum in one operand. So we need a new type of operand for this, which is a stack offset operand. This one does not require a new operand because we need a register operand and an immediate operand. Okay, great. So let's do that. We'll need a new stack operand. And it's going to be a machine operand. And it will always be the size primitives. It's going to be a 16-bit pointer. And it will consist of the stack operand. We might as well pass in the register stack pointer and then the offset, which will be an integer. Okay. So and when we render this, we will we'll first need to hang on to these member variables. And we keep the offset as a signed integer because it is signed. It could be positive or negative. Okay, so we'll first, when we render this operand, we need to render the stack pointer. So let's do that. I'll write the name of the stack register, and then we need to check the value of offset, if it's negative, positive, or 0. So if it offset is larger than 0, then we need to write a plus sign. And then we will write the hex number of the offset, just like that, to the renderer. Otherwise, if the offset is negative, then we need to write a negative sign and then make sure that we negate the offset before rendering it. That should do the trick. And then we're done. So that takes care of F8. This one right here. Let's give that a run and see what happens. Okay, we fail. So something's fishy. We'll have to debug that. Let's make sure we got the right opcode. It's F8. Load HL with SP plus. All right. Oh, we haven't implemented the mutator, of course. So we have the operand that we need to hang on to, but we need to actually generate the operand using this decoder. So here again we have an offset that's a signed byte in the byte stream, so we need to read it. So we'll say if dasm rdr try read byte, and if that fails, then we're out of luck. Otherwise, we have now an offset. We need to convert it to a signed byte like we did yesterday. Now that signed byte will be our, we'll call it integer offset. Okay. So now we have a signed offset. Now we need to create one of these operands. Passing in their stack register. And the offset. I offset. In fact, we don't need the, we can just do this. And the compiler will do the rest for us. Great. And then we add that to the disassembler's list of operands. And we should be good to go. Let's give that a try. Now there's two instructions left. And then we are ready to sort of put a nice bow on the disassembler, at least for now, and start plugging this into the rest of the rest of the Reko environment. Okay, so we have a bug. We're getting a +4 when it should be minus. So what am I doing wrong? So let's see, we're reading a byte, sending into the stack operand, and the stack operand, if the offset is larger than 0, oh, copy and paste, my mistake. Strictly speaking, we are doing a kind of pair programming here, so if you do see me make a mistake, don't be embarrassed. Please chime in the chat. I do appreciate any feedback you might have. There we go, much better. All right, so now this guy is another type of operand. It actually is a register operand and then an integer operand. So this is assigned immediate in the stream. Now we do have a mutator for unsigned. I think it's called D8, right? But in this case, we know that this is assigned, so we probably should add a comment here that says mutator. This one reads a unsigned byte immediate value, and we will create a guy called S8, where S stands for signed, and we'll call this signed byte immediate value. So we'll do it this way. S8. Great. So now we need to use it in the decoder for E8, which was, we have something already called R8. But that's used for something else, I think. Yes, okay, that's used for relative jump, so that's an incorrect. So we'll need to fix that. This will now use S8. Great. So that should give us a signed offset relative to the stack pointer. Let's take a look and see what we have there. So we'll expect something like this. And this is going to fail now because our immediate operand renderer is not respecting the signedness of the operand. It's going to attempt to render this as an unsigned. So we'll see that happening now when we try to render. But we'll fix that. Exactly. So it's rendering as an unsigned 32-bit integer, which is clearly not what we want. So what we want to do then is fix the render in GameBoy instruction so that it respects the signedness here. So we'll take a look at the primitive type of the operand, the width. So we'll say if this guy is, actually, do we have a, we don't have an is signed here, so we'll check the domain. And if the domain is signed integer, then we need to do some special casing here. We'll have to render a sign and then negate possibly the number if needed. So if the domain is a signed integer and the number is negative, then we render a minus, and the minus is, yeah, renderer right car, a minus sign, and then we take the absolute value of number and render it in hexadecimal. Otherwise, if the number is positive, we could choose to render a plus sign here. It is redundant and not necessary. I'll skip that, in fact. I'll only render a minus sign if we are negative. And let's just do that for shins and grits. And now we'll run all of our unit tests and see what the state of the world looks like. Okay, we have 3 failing tests. Bit has now a little trailing H. It's a matter of style. The H is kind of an unnecessary digit, or numbers less than 10 clearly don't need a hex suffix, but we'll add it there. Okay, that's a problem. Okay, so let's go back. Let's make sure that the numbers that we are generating are never larger than so we do want the uint here, but then we'll want to cast the number to an integer, a signed integer here. Actually, assigned short, because these are going to be at most 16-bit. So we'll say number equals short number. So I will do a job, and then okay, let's just do this. Signed number is that if the signed number is less than 0. Yeah, that's the right way to go. And then we'll render the signed number. Else render the unsigned number. Okay, and this code can be cleaned up later once we get the unit tests to pass. This final one is another addressing mode, which again is a little bit misleading. It looks like it's reading at address 0 A7. In fact, it is reading at the same high page that I mentioned earlier at address FF00, but that FF00 is implicit in this instruction. So, but we do need to write the mutator for that last addressing mode. So let's find him, which is over in the disassembler class, A8. So we'll put him with the other memory access guys. A16, so this is like the little brother of this, where instead of reading 16 bits of address, we only read 8 bits. Alright, and so this offset is no longer a uint, it's a byte. And it's a unsigned byte. And let's change that to B. Offset is B. Okay. Yes. So the disassembler now, at least in theory, is complete. It disassembles all the instructions of the Game Boy instruction set, as far as I can tell. We have no unimplemented instructions anywhere. It knows how to handle both the baseline decoders and then also the decoders that take the CB prefix. So we are now ready to introduce this new class to the rest of Reko. Currently, if you try to load a binary and then use this disassembler, there's no way to select the Game Boy processor because we haven't told Reko about it. So, like in a true cooking program, in advance I've made some changes to the magic reko.config file, which contains all the configuration information about all of the supported architectures, all the supported file formats. And one of the things I did was I added the architecture, and I'm using internally the LR35902, but externally we'll use the word Game Boy to identify this architecture. So there's that. Then we have to tell the build system that, by the way, whenever the Game Boy assembly is changed, we also want to make sure that it gets copied into the drivers, the front ends of this. So what we'll need to do is go into each one of these and add a reference to the Game Boy assembly. We'll want to do that for the command line property as well. Oh, nuts. That's not what I wanted to do. I wanted to do this. Clumsy fingers today. Add project reference. Game Boy is right there. Oh, there's some missing architectures. Let's just add those back in while we're here. There's quite a few missing, actually. Oh yeah. Let's make sure they get added back. Okay, great. Do we need to add them to runtime? Let's make sure. Yes, we do. So let's add them here. And yeah, we are missing a few here as well, I can tell. So let's just add them. E-tracks. Game Boy. LEM. The list is ever growing. Okay, great. Now, there is another file that we need to update, and that is the common items. And here we'll find the environments. That's the metadata. Here we go. So we'll use this one as a template. We have no metadata yet, but eventually that will happen too. Okay, so we are almost, we're actually ready to go. So let's do a clean build of the project to make sure we pull in all these files. So now ideally we should be able to pick our new disassembler from a list of supported architectures when we try to open that binary. And I promised that if there was time, I was going to start writing a very crude ROM loader, and I think we do have time for that now. So what I'm going to do is I'm going to load the ROM file that we have, sample ROM file, as just a flat file for now. I'm going to completely ignore the structure of the file, although a Game Boy ROM is actually a banked file. It consists of multiple segments of ROM bytes, and there needs to be some sort of sophisticated logic to handle that Reko currently doesn't quite support. So we're just going to load in the ROM image as a flat bag of bytes, and then at a later date, support for loading those banks will need to be added. Almost done. Oh, we got some failures. There's a problem with CMake on my machine. That's okay, it's a harmless error. I'll just do a build. This will go away. All right. So let's see if we can load our binary now using our new architecture. So we'll try to open it, and the file format is currently not recognized. So we will pick our architecture, which is right there. And now we get some cool exceptions. This is great. This is actually progress. It tells me that the Game Boy architecture got loaded into memory, but we haven't indicated how a hexadecimal address is to be parsed. So we'll need to implement that. That's fairly easy. There's a handy function called try. Let's just stop this and let the IntelliSense kick in here. So on this platform, addresses are 16-bit. All right, let's run that again. That was, by the way, one of those many methods of the architecture class that we still hadn't implemented. All right, let's get rid of some of these breakpoints. We shouldn't need them anymore. All right. So something is wrong. FF. Okay, I know what the problem is. FF is an invalid opcode, if I remember correctly. And no, it's not. It's an RST instruction, so that should have succeeded. So for some reason, after reading the ret instruction, it goes off the rails. So let's try to be curious about what's going on here. Let's turn on all exceptions, making sure that there's no exception being thrown and discarded. And let's click on this. Okay, something's really confused. Could it be that the length calculation is going askew here? Let's put a breakpoint right here. Yes, so here's the bug. I've inverted the sense of the computation of the length. I'm taking the address of the reader where it was before we read the first byte of the instruction, which is going to be a low number, and then I'm subtracting a larger number. So this is always going to be a negative, so the length is always negative. There should be a check somewhere to make sure this never happens. Let me just fix that real quick. I'm glad I wish they all were this easy to find. Let's get rid of that breakpoint. All right, let's try this again. Let's get rid of the breakpoint. That's more like it. Okay, so last time we viewed the file, we were looking at it through the eyes of a Z80 disassembler. Now this is the new disassembler, and maybe it will show us different contents now. So if we go to address, was it 150? 150. That was where the boot ROM started. Okay, so this looks reasonable. Disable interrupts, but that was the same in Z80. But here we have that juicy new addressing mode, load HL-A. That does not exist in Z80, and that caused the Z80 disassembler to derail. But here we are safely decrementing of B and then jumping back. So there's a little loop here that is loading stuff from, actually it's writing stuff to the ROM. And as an aside, what that actually is doing is creating bank switches on the ROM. So it's traveling through all the pages of the ROM and flipping them on through the window in the address space where the bank is mapped. Okay, so yeah, this looks very reasonable to me. This looks like perfectly fine logic for an Z80-like computer. So that's all fine and well, but one thing annoys me, and that is that we are not automatically loading the file. So we need to create a loader for this particular image file format. So what Reko does, what you can do with Reko is you can define a loader as either Reko identifies the type of file based on either some magic cookie or sequence of bytes inside the file, like the classic MZ header of x86 executables in Windows, or if it cannot find a well-known signature, it will then base its identification on the file extension of the file, which is a little bit more fragile, but in a pinch will work. So again, I took the liberty in advance of adding a pattern to the configuration file here, which is this blob of bytes. And I realized I made a mistake, because in the documentation for the cartridge header, which is essentially what we're looking at here, it's a dump of a cartridge, it states that there is a blob of bytes that define the bitmap of the Nintendo logo at address 0104, and if these bytes are not present, then the Game Boy will just lock up. So clearly this is used as an identifier to identify the file format. So what we'll do is we'll use these bytes as identifiers, but also we have to make sure that we read them at address 0104 of our file, and we're not doing that right now. We're reading them from offset 0, and that will fail. So we'll just make sure that we specify the correct offset, and then we need to implement a new type called GameBoy.loader. So that would be the loader for Game Boy ROMs. So let's go ahead and add that into our Game Boy project. So this will be a class called loader. And it, as usual, will derive from a abstract base class. In this case, it's called image loader. An image loader knows how to take a raw blob of bytes and return something structured back. And we have a bunch of unknown or abstract methods that we need to implement. Now, the preferred base address for a ROM is apparently address 0, so this is pretty easy. We'll just specify that we want to be loaded at that address. Then we have a constructor we need to implement. Wait a minute. Oh, there's a setter. Well, how about that? For now, let's not support the setter. And the reason why I'm not supporting that is because ROM images are not relocatable. Because of the presence of all those absolute addresses, it's meaningless to relocate a Z80 program. You just can't do it. So we need to implement a constructor for this class as well. So there is the ubiquitous services handle, which we're going to be using in a short while. We have the file name of the file, and then the raw bytes of that image of the file. So we'll just pass those on to our parent class, and really there's not much else we do in the constructor. But now we get to the loader. So this loader will now, it needs to create a program object, and this is a very central object in the decompilation process. So once you've determined the file image format, typically the file image format will either implicitly or explicitly define a processor type and a some sort of environment. So for instance, in a PE executable, the PE cof header will contain a code that indicates this is an x86 image, or this is a MIPS image, or an x86 64 image. ELF image files do pretty much the same thing. And in this case, this particular file format implicitly defines the Game Boy processor as its architecture, because clearly this is a Game Boy cartridge ROM, and so there is no other possible architecture could be. So we're going to go and ask Reko to load that architecture using the configuration file. So we'll need the configuration file service, and that is something we grab from our services handle, and we say I require the iConfiguration service. So I need to talk to the config file basically and obtain something from it. And then we ask it, hey, get me the architecture whose name is, and we'll use the technical, scary name that I can never remember as the key for the architecture. Now, that should work. If it doesn't work, it will throw an exception. So we expect this to work. So now we have an architecture. We also need to create a environment, and that's the Game Boy environment. And so we haven't created that yet, so we'll need to do that. We'll call it the Game Boy platform. So a platform encapsulates all the aspects of a particular computing environment. So typical such platforms are Windows or MS-DOS or generic System 5, and in this case Game Boy. So we need to implement or extend the platform abstract base class, and as usual there's a pile of these methods that we'll have to implement. I will just get away with not implementing, or implementing as few of these as necessary to get this to work. And then we need to have a constructor, and it, as usual, wants services. It needs an architecture and some sort of platform ID. That would be Game Boy. All right. Let me just check one thing. Yeah, okay. So I service provider, I processor architecture, and we're good to go. All right, so here again we don't do a lot until asked. So now we've defined the platform, the environment that the Game Boy defines, and there's a few methods here that if we need to implement them, we will. Let's kill this file, and then we can go back to our loader now. So now, after creating the architecture, we now load the platform. Again, we expect that to always work in a properly installed environment. And then the platform itself is platform def.load, and we pass in our services and our architecture. Okay, so those two steps are necessary for the generation of one of these program objects, but then the final step that we need to do is load all the segments. And as I mentioned earlier, this banked architecture of the ROMs is a little bit complicated, and Reko is not really ready to handle that yet. So we're just going to read in the first 64 kilobytes of this file and just hang on to them as a single segment. So we'll take the we'll create a new image, which is going to be the minimum of 64 kilobytes or the size of the actual ROM image. So we'll call that image is a new byte of either the raw image length or 65K, which is 0x1. And the reason why I'm using this particular magic value is because the Z80 can only address 64K of memory without using mechanisms like banking. Okay, something is unhappy here. Okay. Well, let's just assert that we load this. Okay. So now we have an image. Now we need to create a segment for that image. And so we'll need to give this image a name, and we'll just call it ROM. It's just the name of the segment. And we need to create a memory area, which is the combination of the raw bytes that we just loaded. Oh, of course we need a copy. Copy the bytes from the raw image from offset 0 to the new image at offset 0, and the length is image.length. Okay, so now we'll need to create a memory area. That is a new byte memory area. Byte memory area is implying that the data that is being encapsulated is byte addressable, which for most modern architectures is the case. As I mentioned last time, though, there are some architectures where we cannot address the data by byte. You have to address it by 64-bit quantities like on Craze, or 16-bit quantities like the military standard 1750A processors. But here we have a byte-oriented machine, so we'll specify the base address, which is going to be 0, or my preferred base address, and then the bytes, which is an image. Now we feed that to the image segment, telling it here is a chunk of memory, and we're going to make the access mode read-only, or read-execute actually, like that, because it will contain executable code, but it won't be mutable because it's ROM. And again, I'm making no effort here in trying to load any RAM, and that is future work. So we have an image segment now. Now we need to feed this to a class called an image or a segment map, which describes the layout of all the segments. We have a single one in this case. So the segment map takes a list of image segments. So we'll just feed it the single one that we've got here. And now we're finally ready to create a program. So we will create a program, and that is an object that takes a segment map, an architecture, and a platform. And we've implemented the program method. Later, we are given the opportunity to relocate this image. This becomes interesting when you're loading dynamic libraries in Windows or shared objects on Linux and other Unix-like platforms. But in this case, there's no need to relocate anything. However, we do want to be able to tell the caller, I know where this program begins. And if you read the documentation, it states that the program always starts at address hex 100. So we need to create a symbol that specifies the starting address. So let's go ahead and do that. We'll say that start is an image symbol of a procedure that is programmed in the architecture that was specified in the program object. It is at address hex 100, and let's give it a name like start for fun. Maybe even ROM start or ROM init. Clearly that can be changed to more appropriate. If you're aware of a better name for this, for the Game Boy, I'm more than happy to change that. But we now have a symbol for this entry point of this function. And so we need to create a relocations results which will contain the this entry point. So we'll say new list of image symbols, and there's only one known symbol, which is the start point. And then we'll create a list of a sorted list of symbols. Again, there's only one known symbol. And that concludes the relocation, quote unquote. All we really did was create a symbol and then return that symbol. And if everything now works, which it won't, then when we now launch the file or try to open the file inside of Reko, it will automatically load up the environment, load up the architecture, and display the results. So let's give that a whirl. And it's probably not going to work, but it's always fun to test it. See where it blows up. So here goes. Ha! First try, how about that? Nice. Okay, so here we have our image, ROM image loaded, and I think it's got truncated. Oh, a little bit of garbage at the end there. That's no worries, we can fix that later. But yeah, so we have now a working, although very, very crude and obviously incomplete ROM image loader. And we are in a good position now to implement the next phase of a full architecture implementation, which is what Reko calls rewriters, but which the literature calls lifters, because the whole point of the decompilation is to transform machine code into something higher level, and in order to do so we need to perform analysis on the machine code. And in order to avoid having to write a separate analyzer for each one of these architectures, we need to convert the machine code into a common language, which is called IR, or intermediate representation. And creating such a rewriter is going to be the next step. And that's going to be a fairly hefty step. It takes a lot of attention to detail because you have to match the specifications of the processor very accurately in order to get satisfactory results. But we are now ready to start implementing that, and that will be the topic of a future session. So there you have it. We have a working disassembler, and it's disassembling all the instructions of the architecture. And we have a crude but functional ROM image loader that understands this architecture. So after a bit of polishing of the source code, I'm going to do a push of this code tonight, my time. So if you are curious and want to play around with it, it will be available in maybe half an hour. And since we have a few minutes, if anybody has any questions, now is a great time to type them in the chat, and I'll do my best to answer them. And if I don't hear any questions, then I think I'll call it a night. It's been a very productive night. I think I'm very excited of the fact that I was able to write this in a net of, let's say, 2.5–3 hours. It's a full from scratch almost Granted, we knew a little bit about the previous or the architecture of Z80 helped me a lot since I was very familiar with that architecture, but I hope that you can see how relatively straightforward it was to do this. Now granted, this architecture is small. It can be written in maybe 2,000 lines of code. A larger architecture like ARC64, the ARM V8 64-bit architecture is a much larger investment of time. And the disassembler is just the tip of the iceberg. The real work is writing these rewriters. So I don't see any questions. So if that's the case, then I will say thank you, and you can always reach me at Discord or the Gitter chat. And thanks a lot for your patience, and I hope this has been worth your while. I'll say good night.